good weekend? Okay, let's get started with logistics. So if you haven't noticed, Exam 2 grades are available on Canvas. And just like last time, you can, if you click into your grade, you can look, and on the comments, it'll have the PDF of your exam along with the annotated grades on it. So please take a look at those if you haven't. And if you see anything you have a question about, or if I did math wrong, or just messed up and marked something wrong, just send me an email, let me know, and I'm more than happy to fix it. If I made a mistake and gave you points when I shouldn't, I recommend not telling me about that and just keep the points. But overall, everybody did really well. The grades were good all around on Exam 2, almost too good. But I'm fine with that. I'm happy when you're doing well, and if everybody does well, even better. So those grades are up. Please take a look. For us, for our next 2 weeks, so here we are on Monday. We're going to start talking about graphs today, and then we will talk about graphs for the rest of the week. You'll find that graphs are quite a large topic. You could take many courses just in graphs alone. And I do recommend, if you get a chance to take like a graph theory course, it's a really interesting subject. And there's just a ton of stuff that can be done with this data structure. And it's actually a data structure that's used a lot. And it's used for things that are important and things that are scary and everything in between. But this week will be graphs. Friday, your challenge 3 is due, and that's been posted on Canvas as well. And then next week, we'll start to talk more about things we can do with graphs. So algorithms that we can do on that data structure, kind of the most important ones first. And then after that, we'll do a little bit more with graphs, and then we'll start heading into hashing. All right, so programming challenge 3. I don't know if you've looked at this yet, but it is up on Canvas, and the demo is Friday this week. So just to quickly look over it. So there's code available on Canvas to download. It's the code for the binary search tree. It's already all implemented. And so what you need to do is take a look at that code, compile it, run it, understand it, all of those things. And then you will need to implement these public-facing versions of the functions. And if you remember, we did that, I think in stacks and queues, possibly. I don't know if we did it on linked list. But essentially all it is like what's provided in the code is there's an insert function that takes in a node and the data. And so what you'll need to do is write the public version, which just takes data and specifies root as that starting node. So that's pretty straightforward. And you'll just do that for all of the functions that are used. As far as what you will do during the demo, so you have those public functions written, and you'll be able to test that with the test code that's provided to make sure it works. During the demo, the TA will ask you to essentially to delete your delete function, and then to rewrite that and be able to explain what it does. So pretty straightforward. Mostly, if you just take a look at the code that's provided, run through it, get some intuition on it. You may want to flip back to like some of the lectures we did on binary search trees. I know it's been a little while, but once you have an understanding of that, and specifically this delete function, that's what you need for this challenge. So hopefully that one will not be too much of a time-consuming thing. Are there questions about that?
Are we just rewriting the delete function the exact same?
Yeah. I suppose you could write it like slightly differently, like stylistically, as long as it does, the delete process. So, yeah, definitely encourage you to just go ahead and take a look at that as soon as you can. just to get that checked off. And be sure to sign up for the demos. All right. Any questions in general before we move on into graphs? Okay, good deal. So if you remember, between exam 1 and exam 2, we pretty much just talked about trees. All of the trees. Well, not all of them, but a lot of them. So now we're going to look at graphs. And so if you remember, the last thing that we looked at was an AVL tree. And it had this property of always having to be balanced with these very tightly constraints. It's a binary search tree that's balanced. Before that, we looked at just binary search trees, which are a little bit more forgiving than an AVL tree because we didn't care about the balance. We just cared about this property of smaller things to the left, larger things to the right, and only having 2 children at most. So a binary search tree. Before that, you might remember that we looked at binary trees, which were even a little bit more relaxed. The only rule we had here was you could only have up to 2 children. Didn't really matter right or left, greater, smaller. And if you remember way before that, we talked about trees in general, which didn't even have the constraint about how many children you could have. You could have as many children as you want, as few children as you want, but you had to be in a tree structure, so a hierarchical structure like this, where you have nodes and they're kind of going down in a directed fashion. So today we're going to talk about graphs, and just to break through, I think some of what we usually think of as a graph, probably pre-computer science or pre-certain math courses, is something like this, like a plot, right? That's probably what we learned like in high school as being a graph. But what we're going to be talking about, and what in computer science, when we talk about a graph, usually what we mean is a structure like this. And if you look at this, it's essentially something very similar to what we were doing with trees, right? So you've got these nodes, and what's different here is that you see things are connected in ways that we would never connect them previously. And so with a graph, that's kind of the flexibility that we're getting. The idea is that we can connect things in lots of different ways. So we're not looking at like these tight constraints of like only this many children or certain properties that have to hold necessarily, like you don't have to be less than your parent or greater than your parent. We're looking at this more general case, right? And so today we're going to just start by kind of going through the basic properties of a graph. Just like trees, there are a lot of terms, a lot of concepts that go along with this. They're all pretty intuitive. So I think that this lecture will be pretty easy to grasp, kind of a nice introduction to this data structure, and hopefully will be helpful as we go on to actually use this in ways that are useful and are used in a lot of things. So basic idea is that a graph is a collection of these nodes, and when it's a graph, we usually call these vertices, so just a vertex, this node, and usually the vertex will have some data associated with it. In our case, it would always be just like letters or numbers or something, but you can imagine any kind of data you want being linked to that. And then, in addition to having these vertices, we have these links between the vertices, which we call edges, when we're talking about a graph. And sometimes you'll see this called an arc, but mostly you'll see it called an edge. And if you're thinking about it, you can think about trees. Trees are a subset of graphs, right? So what we consider a tree can be a subset of what we consider a graph. So it's just a tree is a more restricted version of a graph. So we're kind of going the opposite direction, whereas we got more and more strict on trees and what we wanted to do with them. Now we're just jumping all the way back up to the top, and we're just going to let everything go here and see what we can do when we're allowed to connect all of these things and use those in different ways. So if you want a little bit of a more formal definition of a graph, and this is what you'll see in a lot of textbooks or just in notes, showing kind of more of a mathematical notation for a graph. We generally call the graph G, uppercase G, and the vertices are V, and the edges are E. And so we can define a graph as being a set of vertices and a set of edges together. There are two major types of graphs that we'll talk about, and those are directed and undirected graphs. So if you remember, we did this a little bit with trees in the beginning, but like for this graph, you can see that these edges, they're just links. They don't have like an arrow or anything saying you can only go one way or the other. Now, you can have graphs where these are directed. So you could say, like, if you're at B, you can only go to F. You can't go from F to B, that kind of thing. And notationally, the way that that's written is like this. So if you have unordered pairs of vertices, so when we write an edge, like say we wanted to talk about this edge between B and F, the way that we're going to write it is B comma F. And if it's unordered, we'll put it in these curly braces. And in that case, it doesn't matter if we write B comma F or F comma B. It's undirected. It can go either way. If we're talking about, like if we had an arrow here, say that F goes to B, we would write it in parentheses, and that means that it is an ordered pair, so there is a direction associated with that. And we would write it, if it's F to B, F comma B. And so notationally, if you wanted to discuss this example graph, you could say that the set of vertices is simply all of these nodes that we have here, and the set of edges are all of these pairs, right? So these are just all of the edges that we see here. And this is undirected, so they're in the curly braces, and it doesn't really matter which order they're in. So some more about graphs. When we have a vertex in a graph, right, we have edges that connect it to the other vertices, and we could have, just in a general graph, right, there's nothing stopping us from doing like two edges here, okay? It doesn't make a lot of sense in most cases, but we could have two links between B and E if we wanted. If we have like a set of vertices within a graph, and graphs are a lot like trees. Remember, trees, we have subtrees. We'll like kind of can do the same thing to a subtree that we do to the bigger tree, and you just kind of zoom in and out. Same thing with graphs. You can kind of zoom into sections of it, zoom out to bigger portions of it if you want. When we have the ability, and so like this is an undirected graph, right? So I can go from any of these nodes, either way on these edges. Something like going from A and taking some route and coming back to A, if we can do that, that's a cycle in the graph. So it's pretty intuitive. So for example, one way to do a cycle to A would be to go A, B, E, and then back to A, right? You could also do A and then, maybe B, then C, then D, then E, then you could go all the way around if you wanted, right? You could make these cycles however you'd like. And so this is something that will be important in a lot of problems, is if a cycle exists, how big that cycle is, things like that. One other thing that comes up sometimes with a graph is that a graph can have a self-loop, right? And so there are specific applications where this makes sense. It doesn't always make a lot of sense, but the idea being that you can have an edge, if you're a vertex, an edge to yourself, right? And so you'll usually see it drawn just like that, which is pretty intuitive. And that's just a self-loop that lets you leave the vertex and come right back to it without going anywhere else. Okay, so we want to make a distinction between what we would call multigraphs, sometimes called general graphs, and simple graphs. So with a multigraph or a general graph, we can have those self-loops where a vertex has a loop to itself, and we can have the same pair of vertices connected with multiple edges, right? So here you only see one edge between each. if we have this multigraph structure, it would be fine to have like 500 edges between these for some reason. In general, we don't use multigraphs just kind of in our general introduction to data structures. If you get more into graph theory and are looking at specialized use cases, then multigraphs become more relevant. But for us, we'll look at what's called a simple graph. And in simple graphs, we don't allow self-loops. So we can just kind of ignore that. That's not going to happen. And we don't allow repeat edges. So only ever have one edge between these in a unidirectional graph. So we mostly care about simple graphs. And that brings us to the idea of directed and undirected simple graphs. So when we say that we can only have one edge between these vertices, in a unidirectional graph like this one, it's just that one edge. However, in a directed graph, we can have two edges in opposite directions. That's okay. And so you can see why that makes sense, because in this case, whatever this is representing, it's fine to go from A to E and A to B, but going from B directly to A or from E directly to A is not okay. However, B and E can go back and forth however they'd like. And so that's what that represents. And so anytime we have a directional graph, you'll see arrows like this, and that's just telling you where you can go when you're at a specific vertex. A lot of the graphs that we look at will be these undirected graphs, and so they'll just appear like this, it's just lines, and you can go either direction from these vertices. Okay, so let's go through a little bit of terminology with these graphs. And we'll do a quiz on Wednesday. It will be pretty simple. So what will be on the quiz will be these degree calculations about these vertices. So in this undirected graph, for example, when we have two vertices and they are connected with one of these edges, like A and E, right? We consider them to be adjacent. That's a word you'll see. And we also sometimes consider them neighbors. So neighbors is a word that we will use to talk about them. So an edge itself, so this connecting line, we call it incident with the two vertices that it connects. And that's kind of just common vocabulary that you might see discussing graphs, but it just means that they're connected. So now if you remember, we talked about degree with nodes in trees. And so with trees, we had like the number of children being the degree. For a graph, we have kind of the same concept. The degree is an idea that's centric to the vertex, right? So when we talk about a degree, we're talking about a specific vertex. And so in the example of like the unidirectional, or the undirected graph, these are pretty simple. It's just the number of edges that are coming in to the vertex, right? And so you can see like A has a degree of 2 because it's got 2 edges that are incident with it. B has a degree of 4. And so you might wonder why do we care about this? So as we start to use graphs to solve actual problems, you'll see that a lot of times by knowing the degree of a vertex, we can say certain things about other parts of the graph. We can make certain assurances in terms of the runtime or the complexity, because a lot of times we'll be thinking about how connected could something be, and within the scope of the problem we're looking at. And degree will come up as one of those measures that's very helpful. And it's a very simple measure, but it makes a lot of sense because you are asking how many connections do we have in this case. So similarly, for a directed graph, we have the same concepts. So we have this adjacency concept, and we give it a little bit of a different vocabulary here. So we can, like if we have this direction from A to B or B to A here, we can have A is adjacent to B is adjacent from A, language like that. They're still incident with each other, But when we talk about degrees, now we have two things to talk about, right? So we don't talk about just degree in general, we ask for the in degree and the out degree, which is exactly what it sounds like, right? So like if you look at this vertex A, you can see that we've got one edge that's directed into A and two that are directed out. So our out degree is 2, our in degree is 1. And so this matters a lot whenever we do have something that we're representing that has this directed nature to it. And so one thing that's, we'll talk a little bit about like, applications of graphs, and which there's so many of them. But one of the most common ones that you hear is usually like social networks, right? And so you can think about how this exists in the real world if you think about some of these examples of like social networks, social media networks. So if you have a network, like let's say Facebook or something, where when you become friends with someone on Facebook, right, that link is bidirectional, right? You're friends with them, they're friends with you. That's how that works. Now, if you're thinking about a platform where something like Twitter, X, you can follow people, right? But they don't necessarily follow you back. And so that's something where you could see kind of a distinction, right? Because you have these directed relationships that exist. Are there questions about this in degree, out degree, degrees, anything so far? Okay. All right. So there are some other things we can do with graphs. First of all, just for convenience, a lot of times we will label these edges. And you might see them labeled as numbers, like they are here, just 1, 2, 3, whatever. They could be named, they could have names, they could have letters, whatever. And that's usually just so we can talk about them easier. So if you see diagrams like this, a lot of times that's just the names of these edges that we've added. The other thing we can do that's interesting and useful is we can take these edges between these vertices and we can assign them a weight. And that's kind of the most generic way to put it. Essentially, we can give them some kind of value or cost or something associated with them. And so like an application where this makes more sense might be, like, imagine if these vertices were airports, okay? And you want to move from, maybe like San Francisco to Chicago or something. And there may be a bunch of different flights that can jump you from San Francisco to wherever, but maybe not directly to Chicago, although there definitely are in the real world. So what you would be looking at is how do I get from where I'm at to where I want to go through this graph of all these connected things. And when we're doing something that's real, usually there's some cost. So you may have a flight that has like let's say it takes you way out of the way, right? So this cost might be like the hours of the flight, the duration of the flight, right? Another common one is like if you're doing like a GPS, like you're mapping. These could be, the distances between two waypoints, and it could be, in like a lot of real applications, it's not necessarily just one weight. It's like some computed heuristic, right, of some kind of cost associated with traveling this direction in the graph. And so a lot of algorithms that we work on are all about finding those optimal paths through these graphs. And to do that, most of the time there will be some weight associated with moving from one vertex to another vertex. In the case of a directed graph, there may be different weights for each direction between two nodes. And you can think of kind of all the applications where this will show up. So in the case that we are working with weights and we're looking at like a diagram of this kind of thing, you'll usually just see the weights written like W equals or some other identifier that lets you know that that's like the cost function associated with it. A lot of times if like you are working on a specific problem and like it's about like traveling down a road or something, you might just see like how many miles it is between these two, just listed on the edge. And so that's something that usually we'll take into account when we're running some algorithm to move through the graph, or sometimes what we want to do is look at constraints that exist in the world. So kind of some interesting problems that we can look at is if you imagine like that these represent, maybe physical locations in a building, right? And so what we can see kind of intuitively is that we probably get a lot of traffic through B, right? Because we've got kind of all of these nodes making it central. And so we can ask questions, like suppose we're remodeling an airport or something. We can say, okay, we've got these terminals here and here, it's connected this way. If I remove this node, I have to shut it down to do something. What's going to happen in terms of where that traffic flows throughout the rest of this network? And so those are the kinds of questions that can be answered with graphs. And in that case, you can have a lot of different factors with these nodes and with these edges that you take into consideration as you're weighing that. And so there are a lot of algorithms involved with manipulating graphs and what they can do. And there are a lot of problems in computer science that can be reduced to graph problems. And so that's very nice as well. So we have a concept that we've been talking about without giving it a real name, I guess. So the formal name is a path. And a path is just a ordered set of edges within the graph. And that gets us from one vertex to another vertex. And so you can see, like, if we wanted to go from A to C here, there are many paths to do that usually. You could go this way, you could go that way. And if you're looking at just like the number of hops that you're doing, obviously you would say that going from A to C this way is just 2, while this is 3. But if you had to consider weights that went along with that, you might have like a very high cost here. Like suppose that this is some kind of process that takes a long time to get through. And so it would actually be more efficient to go around this way. So you can see this again, like roads are a great example. If you put like a piece of road under construction or something and you like reduce the number of lanes, you may up the weight there. And then so like your routing algorithm will see that, and so it will decide to divert you on this other path. Even though it's longer maybe, the heuristic that it might be looking at is time. And so that's kind of a weighted idea. So multiple paths usually between vertices. Sometimes there may not be a path from every vertex to every other vertex. And usually if it's so when we're talking about graphs that are not directed, right? If it's a graph that looks kind of like this, that is connected, there will always be a path between these vertices. But what you've got to remember is the way that a graph is defined, it doesn't always have to look like this. We can have what's called a disjoint graph, and we'll look at that in just a second. And in that case, no matter if it's directional or bidirectional, then you can have these conditions where you may not be able to get from one vertex to another. So here is the example of a disconnected, undirected graph. So this is one graph still, right? And this holds to our definition of a graph, because our definition just says we need a set of vertices and a set of edges. It doesn't say that they all have to be connected together, right? And so we would call this a disconnected or a disjoint graph. And as you can see, there's not a path from every node to every node, right? So if you're in A, B, or E, you're not going to be getting to C, D, or F in this case. But this is still one graph. And so this can come up, again, if you think about the example of like social networks, right? You can have kind of networks of people that are not connected to other networks of people. And so they are kind of these disjoint segments of the graph. So that's something to keep in mind when we're talking about undirected graphs. Now, when we have a directed graph, it is much easier to kind of have the intuition that there may not be a way to get from one node to another, right? because directionally you may not be able to do that. So in this example, you have like A. Let's like say you're at node A or vertex A. Sure, you can go to C, you can go to E, but from C you can only go to B, and then you can either go E or A. From E you can't go anywhere, so you're just done. So these kind of have like this one-way nature to them, but that prevents you from being able to always get to every vertice from every other vertice in the graph. And so this is a whole other set of problems that come up that have to be solved, and that's about kind of being able to reach through the graph, whether it's possible or not. So we have some more concepts here about graphs and specific types of graphs. So for a connected graph, we say that it's connected if we do have a path between any two vertices, and a path meaning it could be multiple edges, so it doesn't have to be a direct link, right? So just that we are able to get from anywhere to anywhere by traversing the edges. And it's fine to have cycles in that as well. Another concept that comes up occasionally is what's called a free tree, which is a connected graph, but it's not allowed to have cycles, and it has to be undirected. And the reason that that's kind of got its own name is that it comes up frequently enough that it's a special case that we have algorithms for that, and like if we see something meets that criteria, we know we can apply certain things to it. So a forest, sometimes you'll see a forest, so lots of clever names here. That's a collection of free trees. And so these are things to be aware of. I don't want you to worry about like memorizing all of these terms necessarily. Just kind of, we want to know the important ones. We want to know about directed, undirected, degrees, kind of the common things. Free tree, forest, it's good to know that that stuff exists. But honestly, it's kind of the thing where I usually have to like look it up and check and make sure that, something's meeting all the criteria or not. And there are, of course, a bunch of other concepts that we can apply to graphs to label them in specific ways. So, one that we should, this one you should know. When you see that a graph is called strongly connected, that means that every vertice is connected to every other vertice directly. And so obviously that has a lot of implications to it when you're solving some of these problems. The ability to go from any vertice to any other vertice on one edge is convenient and interesting in a lot of cases. Okay, so now we're going to move kind of into, this is more where we start to talk about doing interesting things with this data structure. And one of the first things that we can think about when we're looking at this data structure, apart from just kind of exploring it and seeing what's connected to what and what weights exist there, is we can think about ways that we might be able to do something like, so let's say visit every vertex in this graph without forming a cycle. And so that is something that actually is quite interesting and quite useful to solve a lot of problems. So if you look at this graph here that we have, you can see if I were just to follow the dotted lines, I can visit every vertex in the graph. And what you may notice is there are other configurations of this I could use to do the same thing. And so this is what we call a spanning tree. And kind of the intuitive way to think about that is that it spans through all of these vertices in the graph. And obviously you can have multiple of these for a given graph. And this turns out to be something that's quite useful because a lot of times we care about visiting all of these vertices for different reasons. And then we have something called the minimum spanning tree. And the minimum spanning tree is essentially the same exact thing as the spanning tree, except we're going to consider weights with it. and we are going to optimize on that. So we want the lowest cost path that visits all of those vertices within the graph. And we will talk specifically, we'll do at least one lecture, maybe two, on minimum spanning trees, because they are very useful and a very important part of working with these graphs to do useful things. Questions so far about any of this? I know it's kind of just like a information dump about graphs. Okay. So talking a little bit about applications of graphs. This is one of those data structures where there are just so many things that use graphs. And so it's hard to pick. I think social networks are the one that gets the most kind of business these days. But really, they're not that interesting in comparison to some of these other things that we do. In the world of kind of computer science and programming, we actually use graphs within programming languages to do things like automatically take care of memory. So, you know, like when we're writing C++, we do have to manage our memory quite a bit, typically. A lot of other languages will have kind of this dynamic, automatic, you know, management of the memory, so that like when you're done with something, when it goes out of scope far enough, that memory is given back to the OS or given back to the runtime to reuse. Graphs are used as a representation internally with the runtime to determine if like those variables you're using are still connected and linked to what you're doing. And so that is one kind of like in the field application that we have. Now, obviously, graphs lend themselves to networks of any kind. In fact, you may see graphs called networks in some fields, but you can imagine this being a network of anything you would like. It can be roads, it could be data that's going between data centers, anything like that. That can be done as a graph. Things like if you're designing a wireless network and you want to know where to put cell towers, right? And so you're placing them and looking at these different weights and constraints and how they interact, and that can be modeled and is modeled as a graph typically. Other things where graphs are useful, so any kind of transportation network, obviously, so like airlines, this is how it runs. This is how we do those calculations. But also things that you might not think about, things like fraud detection. This is a pretty common way to do this. So you can kind of make these vertices, different things. You might even think about this as like, I don't know, if you're just doing like basic credit card fraud detection or something, maybe these are places that the credit card is used. And so for a particular card holder, you probably have a graph that looks a certain way, and it's kind of obvious when a anomaly jumps out of that graph and it connects to another cluster. Even more so, like if it's part of a concerted effort for fraud, where a bunch of things suddenly link where they shouldn't link. And so it should go without saying that this has tremendous applications in surveillance and analytics, and whether you're an advertiser or you are some kind of national security agency that's interested in what people are doing and characterizing that and correlating things, graphs will represent all of that. And the same algorithms we use to make sure that you have the best set of airline flights can also be used to do quite a few other things in terms of finding specific vertices or entities in the graph and determining how they're connected to others. So also this is used a lot in like genetics. So anytime you see some of the a crime solved by like the DNA ancestry or something links that no one was expecting, that kind of structure works with graphs and shared portions of DNA and linking those together. And you can also see this kind of used in applications that have to do with like governing, like, a residential area or a city or something, redistricting political zones. This kind of thing is used there too. So graphs have so many applications, and you can gain a tremendous amount from them. And especially what's interesting about them is that they apply so much to the kinds of data that we collect a lot of today. So if your interests are in kind of areas that deal with like massive amounts of data and getting meaning out of that data, graphs will probably be a big part of that, depending on what it is. But there's definitely, there are great things that are done with graphs and there are horrible things that are done with graphs, but at the end of the day, the graph is a tool, and it's a pretty useful representation of data. So I want to just think for a few minutes about how we would represent a graph within, within code, on the computer, as a data structure that we implement, how we might go about doing that. And so kind of one of the most basic ways we could think about this, right, is we could just say, okay, we want to represent this graph. Maybe we just make an array, and in our array, we'll just have an entry for each vertex, and then in that entry, we'll have a list of who it's connected to, okay? So this is an adjacency list approach. And there are certain advantages to this. There are certain disadvantages. So when we talk about graphs, we care about the two things we always care about. We care about space, we care about time. With something like this is, in comparison to other approaches, this is a decent way to do this if we care about space quite a bit. So when we care about space is when we have what we would call a sparse graph. And it's a graph where there are not a lot of connections between every vertice. You might have a ton of vertices and just a couple of edges between each. A lot of them might be a long chain or something. So storing just the neighbors for each vertex makes sense in terms of saving space. However, you can imagine that this has some implications in terms of runtime when we want to see who the neighbors of a specific vertice are. And depending on how we implement this, that will affect this. When we talk about runtime related to graphs, we talk about it in terms of V vertices and E edges. So you'll see the big O notation will be given in terms of V and E typically. And we'll get into that more as we talk about graphs this week. But this is just one kind of basic idea, and this works well for a lot of graphs. And it's kind of the intuitive way. Another way that you could do this that might be useful is you could just make a two-dimensional array, right? So what you could do is have rows and columns here, right? And let's just have one entry for each vertex on the rows and the columns. And then within each grid, we either say it's connected or it's not connected, right? And so if we want to know if two are connected, we can simply index in on those two vertices and see, is that a 0 or a 1? You might think about this a little bit in terms of if it's an undirected graph, this will be symmetric, so you'll waste about half of the space here. If it's directed, though, then this has meaning in the order, and so it will not be symmetric. You could also store things here that are not just yes or no, right? You could store maybe weights here or something like that. The disadvantage here, obviously, is that how much space are you using? It's always going to be, V by V, so V squared space that you're using. And if it's a sparse graph where there's not very many check marks, well, you've allocated a lot of memory that you're not using. And so what we'll find as we look at other ways of representing graphs as well is that it is often a trade-off that's made when you think about the data that you have in your graph, right? So it's not completely set apart from the actual application, right? A lot of times you need to know, is it sparse data, is it dense data, What am I going to be working with? That will inform what you choose to represent the data structure. So that's where I want to stop today. On Wednesday, we will have that quiz, and that will just be about the in degree and out degree within a graph, so it should be pretty easy and quick. And then we will continue talking about actually implementing some graphs and some of the interesting applications of graphs. So I will see you on Wednesday.